Hello, good morning. Let us now start with the DSA CC lecture. So let us now start with the DSA. So today we will see the topic of stack and queue. So stack and queue is an important data structure which is of linear type. So we will go through this data structure and it will be useful for your future lectures as well because both this data structure is used for further concepts. Now today's agenda is going to be stack, queue, DQ as well as monotonicity. So we will go one by one and we will do some problems on each. So first we will go through stack. Now what is stack? So the stack is in first out. So a stack is a sequence of items that are accessible at only one end of the sequence. So like let us go through an example to understand it well. So let's say this is your stack. So here you are pushing one element at a time. So this element one, element two. So element one will be pushed at the very start, and along the time you are pushing more and more elements. So the last element you are going to push is element 8, and the element 8 will be at the top. And whenever you want to retrieve some particular element from the stack, then element 8 will be at the top. So you are going to retrieve the element 8 first. So basically, you are following a LIFO policy. That is, the last element which you are going to put is going to be retrieved first. So element 8 was at last, so element 8 will be retrieved first. So what are the operations which are present in the stack? So first of all, let us push. So whatever an element you have, you will push it to the top of the stack. So here the element 8 will be at the topmost whenever you push element 6, 7 and then 8. Now what pop? So in the pop operation, you are going to retrieve the element which is exactly at the top of the stack. So element 8 was the last element which you pushed into the stack, so it will be the removed the first. The top is basically, it is just used to see the element which is present at the top of the stack. It is not for retrieving the data. It is just for getting the data, but not, you are not removing it from the stack. And empty is just for checking the stack whether it is empty or not, and it is useful for um, checking before doing pop and top operation. Otherwise, you will land up with some issue. Which now this is just a variable name, and int is nothing but whatever the data type which you want, whatever the data type of the whatever the data type you want to insert on the stack. So here I want to insert an integer on the stack, so I am using int. So first of all, I am doing st.push phi. So that means basically I will push the phi as an element on the stack. So I have pushed phi on the stack, and my top pointer will be on the phi. That is st.top is equal to phi. What I told you before, that top is nothing but it basically gives you the element which is present at the top of the stack. So you will be getting the phi. Now again I am pushing 2. So st.push 2. So my st.top will be now 2 because 2 I am pushing it on the top of the stack. So basically above the 2, above the 5 you have 2 now. Now once you have done this, we will do st.pop. Basically you will retrieve the topmost element from the stack, which is now 2. So once you remove 2, again the top will be at 5. Top will be 5. And once you do again pop it, definitely this 5 will also be retrieved, and therefore nothing will be left on the stack. So you will get an empty stack, and st.empty is equal to true. So just as I said, it is used for checking the stack whether it is empty or not. So yes, the stack is now empty, so you are getting st.empty as true. Now what will happen if you perform pop and top operation on an empty stack? Then definitely it will lead to segmentation fault, because you are trying to access something which does not even exist, like there is not a single element on the stack. And similarly, there is one more function which is st.size. It basically tells you what is the size of the current, or what is the current size of the stack. So here, if you do st.size, it should be 1. Here it should be 2. Here it is 1. And in this two cases, that is initially as well as at the final, it is empty. So it is going to be 0. Now, all these operations like push, pop, stack.empty, and then size, what is going to be the time complexity of all of them? So all this operation, it takes O of 1 time. Why O of 1? Because you are just going to modify only the top of the stack. That is this. You're basically operating everything on the top of the stack, and you're not dealing with anything anything rest, and therefore you don't require any iterations or sort. Now, unlike array or linked list, you don't need to basically shift an element. You just pop this, pop 2 or pop 5 and so on. So basically you're performing on the uh, top of the stack, so you don't require any iterations or shifting of element, and therefore it all takes O of 1. And that is the reason why it becomes very handy to use stack in various scenarios. Like in the future, you are going to study recursion and backtracking as well as DFS. So stack is going to be used implicitly as well as explicitly, which you're going to be see later on. Now, how it is implemented? It is implemented using usually it is implemented using arrays or even linked lists. Now, our session is going to be focused on problem solving, but if you are interested, then definitely check it out. Any doubts till now? Yes. So in the pop operation, you are basically wait a second. So in the pop operation, you are literally just removing the entire element. That is here 2. So 2 was at the top. So you are just removing the 2 entire element, that is 2. So this is going to be pop. So here it is st.pop. So the 2 is removed. But for st.top, you just want to check what is the element at the top of the stack. So here, if I do st.top is equal to 5, the 5 won't be removed. It is just for checking what is the value present at the top. Uh, is it now understandable? Okay, great. Now let us pop removes as well as returns the value. Top only returns the value. Okay. So all doubts are now cleared. So I will be now going through some, let us solve some problems now. So first problem is valid parenthesis. Now given a string S which contains the characters, so you have open parenthesis, uh, closing parenthesis, open curly brackets, closing brackets, open square and closing square. You just have to determine whether the string is valid or not. So any input string is valid if the open bracket must be closed by the same type of bracket. So basically, if you have a open parenthesis, then it must be closed with the corresponding parenthesis. Like if you have and it Okay, so any input string will be valid if open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order, and every closed bracket has a corresponding open bracket of the same type. Let us go one by one what it actually means. So whenever you have an open bracket, it should be closed by the same type of bracket. That means if you have an open parenthesis, it must be closed with the corresponding parenthesis. Like for curly brackets, it should have a corresponding closing bracket, closing curly bracket. If you have an opening square bracket, you should have corresponding closing square bracket. And it must be in the correct order. That means like the nesting should be done perfectly. So if you have a multiple open brackets, then one by one you should have a corresponding closing brackets as well. And yeah, so it is the same thing. It will be clear by looking to the example. So here you have an open bracket, right? And then corresponding you have closing bracket. So definitely it is valid. So you just have to return as true. Now here you have a open and closing parenthesis. Definitely, so it is correct. So this part is correct. Now here again I am starting with the opening square bracket. I'm ending with the closing square bracket. Again it is perfect. And again it is open curly bracket and then corresponding closing bracket. So definitely again it is valid. So just have to return true. Now let's say you have this open parenthesis. Now you have the closing square bracket. Definitely you don't have the corresponding closing bracket for the opening parenthesis, nor you have an open square bracket for the last character. So definitely it is false because it's not at all valid. And finally here in this example you have a open parenthesis and then you have square bracket, opening square bracket, then you have corresponding closing brackets. So here the nesting is done, but it is done, so it is correctly done because here you have open square bracket and then corresponding square closing bracket, and accordingly you are validating the first bracket as well. So the nesting is done perfectly. You can visualize this, let us say by HTML tags. So basically in the HTML tags, you have to nest it perfectly. For every opening tag, you should have a closing tag. So it is very much similar to that. Now you have to identify whether they are valid or not. So what about the first one?
Not valid.
Okay, correct. So because here it is a closing square bracket, but you don't have that open. And what about second?
Not
Also
valid.
valid.
Correct. Third?
Valid.
Valid.
Correct. Okay, so you all understood, right? So here you can pretty much see that there is some, cannot you observe that there is some LIFO policy being used? That is the whatever the last open bracket you are in, last opening bracket you are saying, you will have a, you will deal with that last open bracket first. That is here you in the second you have the last opening bracket, and correspondingly you have the closing bracket. So basically if there is a nesting of all the brackets, then the most inner opening brackets will be solved first. So definitely here we are able to see there is a LIFO policy being followed, and for the LIFO policy stack is definitely going to be used. Okay, so what is the approach? Now first of all we are going to use a stack to store all the opening brackets. So we are going to maintain a stack of character, and we are going to push all the opening brackets. Where you encounter a closing bracket, you will have to check whether my top of the stack and my current closing bracket, are they matching or not. So if yes, definitely you have to pop the stack. Otherwise, if it is not matching or the stack is empty, that means was no corresponding open bracket, or literally it was an empty stack. You are just starting with the closing bracket. Then definitely you just have to return false. Now at the end, you just have to check if the stack is going to be empty or not. If the stack is going empty, then definitely all the parentheses have been matched, so you just have to return true. Otherwise, you have to return false because all the parentheses have not yet been matched. Have you understood the approach? First of all, I'm going to initialize a stack of characters. I'm going to get the size of the string. So int n is equal to s dot size. And then I'm just going to iterate to the entire string. So if there is an open bracket, I will just simply push it into the stack. So if I'm getting open, square, uh, open parenthesis, square or curly braces, I'll just put it into the stack. Now, as per the second statement, what I told you, that there was an edge case. Let's say if the stack is going to be empty, and if you're getting a closing bracket, then definitely it is false because there was no corresponding open bracket. Now, similarly, this big condition is just for checking that whether your uh, whether your bracket at the top of the stack and the current closing bracket are they matching or not. So if it is a this open bracket and if it is closing, then they are matching, then definitely it is true. Now similarly, this two and this two. So basically, this is just for checking purpose. And if it is correct, just simply pop the stack. Otherwise, they won't be matching, then just return false. And finally, after doing all this operation, you just have to check whether your stack is going to be empty or not. If the stack is empty, then it will return true, otherwise it will return false. So this was the actual logic of this valid parenthesis. Have you understood the code?
Yes.
Okay. Okay, great. Um, so what is going to be the time complexity? So here you are going to traverse the entire string. So definitely O of n. It is pretty much obvious that you are going to traverse the entire string. So time complexity is O of n. What is going to be the space complexity? Now, in the worst case, you have to store the entire string. So let's say you have this open bracket, and so this is what I said about the last condition. So if you just have an open brackets and there is no closing bracket, you are going to be continuously putting into the stack continuously. So basically, you are just going to store the entire string in the stack. So the burst space complexity is going to be O of n. Let us do a dry run. So let's say uh, we will go through this condition. Okay. Let us go one by one example. So here in the first, you had an open bracket. So I am just going to push it. Now in the second, you had another closing bracket. So I am just going to check whether this closing bracket is going to be corresponding open bracket or not. If yes, then just pop. The stack is going to be empty. So you just have to return true. And similarly, let's take another case. If you're going to say this is an open bracket, now I'm just going to push it. Now let's say another open bracket. If then again you just have to push it. Let's say then you have uh, let's say another this bracket that is a parenthesis. Now it won't be matching with the closing parenthesis. This closing parenthesis is not matching with the square brackets on the top of the stack. Then definitely it is wrong. So you just have to return false. Now similarly, let's say if you have an open bracket, you're just going to continuously push it. So let's say you had the string of 5 characters. So you're just continuously going to push it, and therefore you are going to get the space complexity of O of n. And also at the end of the iteration, you are going to check the whether the stack is empty or not. The stack is not empty, so definitely you have to return false. The string is not going to be valid. Uh, Perfectly understood.
Yes.
Okay. What you say? Okay. So first, if okay, the first if is only for like you just have to push the opening bracket on the stack, like because I have to match my closing bracket with the open bracket. So like I will just store the entire open bracket on my stack only. So whenever I encounter a closing bracket, I can easily check with the top of the stack and accordingly pop it. So this is just for checking the.
My doubt is, if you already have checked SOI, then why are you pushing in the stack again? You are checking SOI, right? Acha, okay, I got it. S is the string and temp is the stack. ठीक है.
Okay, temp is basically a stack. So you understood right now? Okay.
Yes.
So any more doubts on stack? I assume that. So queue is again a very important data structure. So the queue follows a different policy. It follows FIFO policy, that is first in, first out. A queue is a sequence of items where elements are added at one end and removed from the other end. So we can go through this example. So here, this is just a queue. So you are like one, you have pushed it initially, then two, three. So basically, whenever you want to push a new element, it will be pushed at the end of the queue. So basically, enqueue is also nothing. Enqueue is basically nothing but push. So you are pushing new element on the end of the queue, and whenever you want to retrieve a whenever you want to retrieve an element, you have to retrieve from the start of the queue. So basically, if you do queue dot pop, so you just retrieve the element from the first. So whatever the element which was first in the line, first in the queue, it will be retrieved first. You can uh, you can get an analogy by considering an example of queue at a ticket counter in railway station. So when the first who is in the line will get the ticket first, and he will be moving out of the queue. So basically, it is the same logic used here. So what are the operations? So first it is push, add an element to the rear. Rear is basically nothing but back of the queue. So whenever you have a new element, you just push it on the back of the queue. So it is pop is removing the front element. So whenever you want to retrieve a new element, you will pop from the start of the queue. So here if I do q dot pop, the one will be retrieved, and now q2 will be at the front. So what is front? Front is the front element. So it is very similar to what stack dot top in the stack. So front is just to check what is the element present at the front of the queue, and back is just to check what is at the back of the queue. So here the front will be 1 and back will be 5. And empty, again it is just a queue is empty or not. Again, let us go through some example. So first I am initializing a queue. Again, it is very much similar syntax with respect to stack. Here you can put any data type, int, character or whatever. Now I will push an element to the queue. So queue dot push file. Now here the head and tail is very much, it's literally the same as a front and back. Head is front and tail is back. So once I push phi to the queue, so the q dot front will be phi and q dot back will be phi. Just like here the pointer is suggesting, head and tail is at the phi. That means front and back is phi. Now, if you push 2 to the queue, then it will be added to the rear of the queue, that is after 5. And now head is again at the same location, that is 5, whereas the tail has now moved to 2, pointing to the last element which is now pushed. So yeah, q dot front is equal to 5 and q dot back is equal to 2. Now, once you pop the queue, then the 5 will be removed and the head, that is the front pointer, will be now pointing to 2 and tail will remain as it is. So the q dot front and q dot back will now point to 2. Now again, if you pop it, you are going to get an empty queue and q dot empty is going to be true. Now again, if you try to do pop, q dot pop, or even if you try to get the front or back of the queue, you will lead to segmentation fault because you are going to access something which doesn't even exist. There are no elements in the queue. And again, the q dot size, it's telling you the size of the queue. Here the size is going to be 1 and here it is going to be 2. It depends upon implementation actually. Like if you implement on your own, it can be for empty queue, you can implement in such a way that it stores -1, but I am telling you in perspective of STL. So in STL, if you do it, you will get some get some very segmentation fault and segmentation fault. So you won't be getting -1. So I'm saying in perspective for STL. Hope this answers you. Okay, now again, all the operations, push, pop, front, rear is empty. It will take O of 1 time. Now why O of 1? Again, the queue operations will modify the front or rear of the queue requiring no iteration. Unlike arrays or linked list, we don't need to shift elements in a queue. Again, so in this data structure, again, you are only going to deal with the front and the back. That is, if you want to pop the element, you will pop from the front. And if you want to push a new element, you are only dealing with the back of the queue. So overall, you don't have to deal with the rest of the elements which are present between the front and the rear. So overall, the time complexity you require is O of 1 for all the operations, including push, pop, front, back, and empty. And again, if you are interested, please go through how it is actually being implemented. It is implemented usually using array or even linked list. Is the queue, and did you all understood queue?
Yeah. Yes.
Okay, great. So number of recent calls. This question looks very lengthy, but trust me, it's not that much hard. So you have a recent counter class which counts the number of recent requests within a certain time frame. You just have to implement a recent counter class. So you have to initialize the counter with 0 recent requests. So initially, you just have to initialize the counter, and currently you don't have any requests. So you just have to initialize it with 0 request in ping. So whenever a new request is added at time t, the t will be represented in milliseconds. You have to return the number of requests that has happened in the past 3000 milliseconds, including the new request. Basically, you have to return the number of requests which lies in which number of requests which have a time frame lying exactly in the range of t minus 3000 to t. It is guaranteed that all the ping requests, they will be in the increasing order, will always be increasing. So let us go to the example. So first is recent counter. You are just initializing a You are just initializing. Now ping is basically first request has come up, so 1. Now as per what they are saying, you have to return the number of requests which lies exactly between the range of t and t minus 3000. So that is minus 2999 to 1. And how many requests are there? Only 1. So you just have to return 1. Now a new request has come, that is 100. So again the 100 minus 3000 is going to be minus 2900. So your range is going to be minus 2900 to 100. So there are two requests, one or 1 and 100 between the two, in the range. So you just have to return 2. Now third request has come, 3001. So again your new range is going to be 3001 minus 3001. So 1 to 3001. And there are how many requests lying between this range? 100, 3001. Again, the last ping request, that is 3002. Here, again you have to 3002 minus 3000, so it is going to be 2. So your range will lie between 2 to 3002, and 1 is definitely not a part of this range. So how many requests are there? 1, 2, 3. So total 3 requests are going to be present. So you have to return 3. Is the question, did you understand the question?
Yes.
Okay. So any idea what logic is going to be used?
Uh,
Okay, so
We can
if
keep dequeuing till we reach the time value, and we increase the count using a while loop for whether the ping lies in the range or not.
okay, any other logic? Okay, so if you notice here, this is very much uh, similar to what we uh, where we taken an example of queue. So here, whatever the request which have come very early, they will be at the front of the queue. Whereas all the last requests, they will be at the end of the request area. So from by checking the difference from the current time frame, we can basically check whether the front elements of the request are they lying exactly in the range or not. So pretty much here the FIFO policy is going to be used. That is first in, first out. So all the early requests, they are going to be removed depending upon whether they are present in the range or not. Okay. So this is going to be the approach. You have to use a queue to store all the request timestamp. Now for each ping request, you have to push T into the queue. Remove all the timestamps which are older than T minus 3000. And you have to return the size of the queue. Now, first of all, whenever a new ping request has come, you will just push whatever the time it is present. And now you have to remove all the timestamps which were in the front of the queue, which have timestamps less than T minus 3000. That means they were all the older requests. So you just have to remove that because they are not present in the range. and you just simply have to return the size of the queue, which are basically the count of all the valid requests lying exactly within the range. Uh, did you understand the approach?
Yes. And this is only works because the requests are like in increasing order of time, right?
Yes. If it was not increasing, then you had to use some other data structure like priority queue or others.
Okay.
So it will be covered in some future sessions. So for now, we have assumed that the ping request will be following a strictly large, will be strictly following a increasing order. So this is the code. So you are initializing a queue. You are initializing a queue, and now I will just push the time into the queue. Now I will basically just check until my queue is empty. As I already said, this condition is very important to check, otherwise you will lead to some errors and segmentation fault. So I will iterate, that is I will use while loop until my queue is empty, and second condition is going to be that queue dot front, it should be less than t minus 3000. So it will basically remove all the elements which were in the front of queue that lies outside the range of t minus 3000. So I will basically remove all those elements using queue dot pop, and for every ping request I will just return the queue dot size. So basically it will determine I am just returning all the valid requests lying within the range. I just ignore the s here. Did you understood?
Yes.
Rest. Okay. So what is going to be the time complexity? Uh,
So often,
yes. So basically here, each request does over one operations on average. It is like every timestamp is added and removed once, leading to amortized over one complexity per request. Now, just don't go much into the details, but basically here I am just going through only one. Uh, you will be removing all the elements at the stack or at the front of the queue, and they are going to be exactly within 3000. At the worst case scenario, you will have 3000 elements. Okay, 3000 different timestamps. So it is going to be nearby over one only, and every single request which you are going to push or pop, you are going to deal with over one only. Like one new request you are adding on the rear, or you are popping the request from the queue. So overall you are dealing with every request only once or twice. uh, okay. Now, space complexity, in the worst case scenario, we will store all the requests within 3000 millisecond. So definitely OAuth and like it is going to be all the requests. Let's say if all the requests they were in within the range only. So technically you are just storing the entire 3000 different timestamps. So definitely it is going to store 3000 values. So number of valid requests at any moment. So you're going to store whatever the number of valid requests you have at current moment, you're going to store in the queue. Is the queue clear?
yes.
Any doubts regarding queue? Okay, great. Let us now start with DQ. So DQ is basically nothing but the combination of whatever we have learned till now. It is a double-handed queue. Now it basically means you can add or remove elements from both the ends. So if I want to push a new element, I can push it on the front as well as I can push it on the back. Similarly, if I want to pop an element, I can pop from the front as well as on the back. Why are calling it as double-handed game? That because you can add or remove elements on the both the ends. Now all the terminologies which you have used till for stack and queue all remain the same. Specification on from where you are going to push or pop. So first is push front. Whenever you want to add a new element to the front, you are just going to do push front. And similarly push back. If you're going to push a new element on the back, just go for push back. Now pop front is if you want to remove a new element, if you want to remove an element from the front of the PQ. And similarly pop back, you have to remove. You will use whenever we have to remove the element from the back of the DQ. Have you understood DQ? Again, the implementation you can go through that. All are clear, right? Stack, Q, and DQ till now. Okay, great. So let us now start with a problem. Now this is going to be slightly difficult problem. So let's start. Now first negative in window size k. Now if you have an array of integers of size n and a window of size k, then what you're going to find is basically starting from the zeroth index for every window, you have to find the first negative number. So here you have 12 minus 1. You require a window size of 3. So the first window is of this. That is 12 minus 1 and minus 7. Size of 3. So here the first negative is going to be minus 1. So you are getting this as an output. Now similarly, let's say this. We are just moving the window. So now it is minus 1, minus 7 and 8. What is the first element? First negative element? Minus 1. Now we will shift the window minus 7, 8 and minus 15. First negative minus 7. 8 minus 15 and 13, 30. First negative minus 15. Minus 50, 30, 16. Minus 15. And if you have 30, 16 and 28, definitely there is no negative number present here. So we will just put it 0 here. So for every window, the first negative number is captured and you just put it into the array. Now, tell me how would you do this? First of all,
Q.
Yeah, right, DQ.
No, Q will work, right? Only Q.
Yeah, Q will also work, correct. I was going to just show after the code, but you have clarified it before. That's great.
So you want me to explain, like, or we will continue? Hello.
You can just give the logic.
We start with the initial window of the first k characters. We push whatever negative numbers are there in the queue. And obviously the first element, the front of the queue will be the first negative number. By the way, in the problem, is it mentioned that there can't be negative numbers, or will there always be negative numbers in the window?
Like there can be no negative numbers as well, and if there is no negative number in the window, you just have to put 0.
Okay, so if the queue is empty, we'll just put 0. Then we have the initial window of the first k characters. Then when we move the window to the next, what we'll do, we will look inside the queue and we will keep removing we will remove the front of the queue if its index is not in the window anymore. For example, from the window of 0 to 3, we go to the window of 1 to k plus 1. So if the front of the queue has index 0, then we'll remove it. And then also, if the k plus 1th element is negative, we will obviously add it to the queue.
Exactly correct. Uh, Very great job. Like this is the explanation which we are going to. This is the way which we are going to solve. So first of all, everyone agrees that the brute force is going to be terrible. Like for every index, you are going to check the k size window. So for 12, I'm again going to see three elements: -1, -7, -8, -7, 8, -15. So for the brute force, you are going to check manually for every single window. So it is going to be n into k. So the time complexity is going to be n into k, which is going to be terrible. So definitely we have to optimize this approach. So for this, we are going to use the DQ data structure. And as was said, we are going to use the DQ data structure to we will just going to check all the indexes whether they lie within the range of the window size or not. So let us now go for the approach. So here we are going to use a DQ to store all the indices of negative numbers in the current window. It is very important we are going to store indices on negative number, not the negative number. Now for each element num psi, you have to remove the
For
indices
every single
out of the
window, so
current
it is
window.
going.
So and in the front of the DQ, and by the way, this DQ you can also solve it using Q as well, but it is just for demonstration purpose how DQ can also be used in all the cases rather I would say. So whenever you have to add you have to remove indices out of the current window, that is if you are in the current index I, so if in the front of the DQ, if you have the indices which lie outside the range, that is I minus k plus 1, that is outside the range of window size of k, then you have to remove all those indices. And if the nums I is negative, then you just add the index to the DQ. Now the front of the DQ always holds the first negative number, that is first negative number index in the window. And if the DQ is empty, you just have to return the 0 for that particular window because there was no negative number in that window. Is the logic? Did you understand the logic? Okay, it might be difficult. I will just go give an example of this. Let's say you had 12 minus 1 minus 7 8 minus 15 30 16 20. So initially what I will do is uh, I am just going to say that uh, let's say we will go through the array. So first of all, it is I'm just going to store all the indices on negative numbers first in the size k. So I'm just initializing the dq first. So first of all, you are having 12. I'm not going to store the index because it is positive. Then you have -1. So -1, the index is 1, right? So I will just push it into the queue. Now you have -7. Again, it is a negative number. So since it is a negative number, I will push its index. So the index is going to be 2. So I'm just pushing it. Okay. Now I have covered the window of size 3 and I am getting a particular first negative element index, that is 1. And what is the one? It is -1. So I will just push it into the answer array, that is -1. Now I will slide the window towards the right. Now 8, the current index is going to be 3. Now I want all the elements which have indices within the window of size k. So it will be nothing but I minus k plus 1. So here it is 3 minus 3 0 0 plus 1. So whatever the indices which lie below 1, it will be removed. So here you don't have any index which is below 1. So there won't be any removal. And at the front you have 1. So it is going to be -1 only. That is the element at index 1 is going to be -1. Now I will slide the window in later. So -7, 8 and -15. Now the I is going to be 4. Now 4 minus 3 plus 1. So it is going to be 2. That means you have to, or you can start the window circle. And now you have second. So at the second index you had what? -7. So you will just push it here. So is it understood? Okay. Let me make it more clear then. Okay, so at what point we are adding new negative numbers? We are adding the negative number exactly when you start at the new iteration. You are not popping the first initial element before. You are first of all checking whether the current number is negative or not. And if the current number is negative, you will just push it. You will push the index at that time, and then you will check from the. Okay, so here first of all I'm initializing a DQ. Now this is a answer array. I'm just getting the size of the array here. Now this is just my pre-processing. Whatever the pre-processing, that means I will put all the element put the, then if I'm getting the first number as negative, you will just push it into the answer array. But you are not even going through the size of 4. You are just looking at the size of 2. So that is the reason why we are pre-processing. Did you understand this? Here I am just going, say, let's say 12 minus 1 minus 7. So I will just say uh, the thing is that, let's say if I check 12, it is not. -1, yes, it is negative. So I will push the index of the negative element, that is 1. Now, technically, if you didn't do the pre-processing, then you could have just say that, okay, this is we are getting a particular array and you are getting the first negative number as -1. So you're just pushing it, but it is wrong because you have just considered only 2 elements. Okay, so that is the reason why I have already gone through the iterate till the k, so that I will just initialize it. I will just go through entire k size window first. That is 12 minus 1 minus 7. Okay, so when it is negative, I will just push all the index. So 1 and 2, 1 and 2. Now, if my DQ is empty, it is a possible that in the first k size window, you don't have any, uh, you may not have any negative numbers. You have to push 0. Otherwise, you can just say DQ dot front, you will get the first negative index and the array. That is you are getting index, and by referencing the index, you are getting the element from the array. And I will push it into the answer array. Now this is the actual for the remaining. Now I will start the loop from k till n, and I will just use a while loop. That is until my deck is not empty, and my dq dot front, it should be less than I minus k plus 1. That means the front of my until my front of the element until the front of the element is outside the range of size k, that is I minus k plus 1. I will just pop them all because they don't lie within the range of the window size. Now if it is 0, then I will just push the index. Now let's say if it is empty, then you will just push it to push 0. Otherwise I will just uh, hmm. so I will just push the particular element of the array at that particular, and once it is done, you can just return the answer. And one more thing, that it doesn't matter actually that whether you are pushing the current element at the before or after, because you just can check the condition whether they lie within the range or not. So you can check this condition before as well as after, it doesn't matter. And I hope it simplifies, or should I go for more examples? Yes, yes. It is only for the first iteration, that is only till the window of size scale. Just as I already told, it is for pre-processing. Otherwise, what happens is that you just have to unnecessarily complicate your final code here, just to check whether they actually have a size of k or not. Otherwise, you will push the negative element, first negative element for a window size less than k. Okay, any more doubts? Is it understandable, or should I take more examples here? Or any doubt in the code? Okay, so it is understandable, I think. Okay, now we will go for the final agenda of today, that is monotonic stack Q and DQ. So basically, they are nothing but they are literally the same what we have learned till now, but it is very much a specific application. That means you have to maintain the order of the elements which are present on a stack Q or DQ for a particular suitable applications, which for particular problems which you are going to see. Now, monotonicity. A monotonic stack Q DQ, it maintains elements in either increasing or decreasing order. It helps to optimize problems related to next, greater, smaller elements sliding into maximum, minimum. So basically, it is always used whenever you are going to get a problem like, okay, for a window size of k, you just have to find out what is going to the maximum for every window size k, or similarly like that. So it is just for optimize. In such cases, it is usual to maintain the elements in increasing or decreasing order, and you have to deal only with the front or back elements. So at on those times, it is very much beneficial to use stack Q and DQ data structure, which is monotonic. Now terminologies will remain the same. There is essentially no changes here. Basically, just maintain the order whether it's increasing or decreasing, and it can be done by push pop operations. So we are just trying to maintain the order by checking the top element and the currently processing element and accordingly we are trying to maintain the monotonicity. Like for example, here it is 1. Now for 7, you can push 7 here because 7 is definitely greater than 1. Then you have 9, so I will push it 9. But once you go to 5, then definitely 5 is less than 9, so I will pop 9. Then I will check 5, is it greater than 7? No, so I will again pop it. So you will just put 5 here. Now then 8, again 8 is greater than 5, so you just simply put it here. Now similarly, monotonic decreasing, you just have to maintain the stack in a decreasing order. So here, let's say you have put the 1. Now here 7, 7 is definitely more than 1. So I will just pop 1 and then add 7. Then you had 9. 9 is greater than 7. I want decreasing in a decreasing fashion. So I will remove 7 and I will add 9. Then again 5. 5 is decreasing. So I can just put it into the monotonic decreasing stack. And then you have 8. 8 is greater than 5. So I will just remove the 5 and I will put 8 here. So here, you might not understand how it is going to be useful. This is just for demonstration purpose, like exactly what is monotonic stack. Similarly, you can have monotonic queue and you can have monotonic dequeue. Okay, so have you understood this monotonicity? Okay, so it will be much more easily understandable. We will understand its importance by going through the problem. So this is the problem, next greater element. So you're given an array A of size n, you just have to print the next greater element for every element. The next greater element for an element x is the first element on the right side of x in the array which is greater than x. If no greater element exists to the right, you just have to consider the next greater element as -1. So basically here in this 7, we will just go through an example. So first it is 7. The next greater element is going to be 12, definitely, because 12 is greater than 7 and it is the closest to the 7. So you just have to say 12. Now, 12, the next greater element of 12 is going to be 1. Of course, now because 1 is less than 12, answer is going to be 20. So here you have 20. Now for 1, again the next greater element you have 20. Now for 20, it is the last element and there is no other greater element beyond that. So definitely it should be -1 here. Now let us take another example. So here you have 1. The next greater element is going to be 5. Now for the 5, 3 is definitely not going to be the answer. 4 definitely no because it is less than 5. 2 definitely no. So you don't have any greater element greater than 5 uh, next to towards the right side of 5. Therefore it will be -1 here. Now 3, next greater element is going to be 4, so answer is 4. For 4, the next greater element is going to be, is it going to be 2? The answer is no. So therefore there is no greater element next to 4, so it will be -1. Again for 2, the next greater element, it is the last element, there is nothing beyond that, so -1. Now here all the elements are going to be same. So here the 5, afterwards you literally don't have anything. 6, beyond 5 you don't have anything. So everything will be -1. Is the question understand? Did you understand the question? Okay. So any idea or approach like how we can do this question? Yeah, sure, you can go.
Uh, the next greater we will traverse from the reverse order So like the last element, there is no element ahead of it, even it is very small. The last element will have -1, and we will then push it on the stack. Then we will go to the second last element. If the top of the stack is greater than it, uh, then we will call it the next greater element of the second last element. Otherwise, we will pop it. So when we are in the middle of the array, we will keep popping the stack until we find an element greater than whatever the current element is. And if the stack is empty, we'll just put -1 for that element, and then we'll push the element to the stack.
Correct, right. So this is the logic of the next greater element. So let us now go through the approach together. So first of all, we will use a stack to maintain the elements in decreasing order. So basically, we will traverse from right to left, just as he said, because we need to find the next greater element. Now, for each element numsar, you will pop the element which is smaller than numsar, because they are definitely useless. Like for example, I will traverse this array right from the right. So initially you have 20. Okay. So initially the stack is going to be empty, so it is going to be -1. Now if you go to right, that is 1. Now definitely on the top of the stack you have an element which is greater than 1. So definitely your answer is going to be 20. And now I will push the current element, that is 1. Now you will go to 12. Now you will check the top of the stack. It is going to be 1. Definitely it is less than 12. So I will pop it off. Now on the stack you have 20. So definitely 20 is greater than 12. So I will just put it here. And I will now push 12 on the stack. Now you are going to the first index. You will check the top of the stack. You will get 12. 12 is definitely greater than 7. So I will push it here. I will just uh, I will just uh, place 12 as the answer for the first index. Now let us go to the approach. Now traverse from right to left because we need the next greater element. For each element, you have to pop the element smaller than numsar. Just as I already told you, if you have a smaller element, they are literally just useless. Like for the 12, the 1 was at the top of the stack, but it was totally useless. So I will just pop it off. And continuously, there can be multiple elements like 1, 2, 3. So all these elements will be basically useless for 12 because they are smaller than 12. So I will just continuously pop it until you get the next greater element, that was 20. Now, if the stack is not empty, then the top is the next greater element. Okay. Now, push the numsar onto the stack for the future comparisons. So definitely, because you just require the next greater element. So therefore, for future comparison, you have to push the current element onto the stack. Now, if no greater element exists, you just have to store -1. Okay, so let us go to the example. So initially you had, we will be going from right to left. Okay, so initially you had 20. Now here the stack is going to be empty. So definitely your answer for the last index is going to be -1. Now once it is done, you can just push it into the stack. So it will be 20. Now afterwards, you will come to the index 2. Now in the index 2, you have 1. Now for the 1, the top of the stack is going to be 20. Now 20 is definitely greater than 1, right? So I will just say the next greater element for 1 is going to be 20. So that is the reason why you have here 20. Now you are going to go for index 1. Now in the index 1, you have element 12. Now I will, okay, my bad. Once you go for the, once you go to the index 1, before that you have to push the element also. So here it will be 1. Okay. Now let's come back to the index 1. Here you have 12. Now I will compare it with the top of the stack. So it is definite 12 is definitely greater than 1. So this 1 is basically useless. So I will just pop it. And the top element is what? 20. So that is the reason why next greater element it will be 20. Now I have 7. So like when I process index 0, now I want to go for 7. Now 7 is less than 20. So definitely the next greater element. Wait a minute, I will just start from the start.
कल रात को when I was walking home, I lost something in the bed and मेरा मोबाइल नहीं मेरा वाईफाई नहीं. She rushed over, desperately trying to push the window aside to save her son, but it was too heavy. No matter how hard she tried, she couldn't move it. Her heart sank. She felt completely helpless. Then she saw it, blood slowly seeping out from under the wardrobe. Her worst fear had come true. Her son was gone. She had only stepped away from home just to call her husband, and in that short time, tragedy struck. But this was only the beginning. When her husband came home and saw what had happened, he blamed everything on her. He was furious and convinced that if she had been watching her son, this wouldn't have happened.
My bad. Okay. Is my voice audible?
Yes.
Okay. Sorry, I was muted. Okay. So let us start from right to left. So here you have 20. Just add -1 because no next greater element exists. Now you have 1. Before proceeding ahead, I will just push it onto the stack. Now I will proceed to index 2. Now on the index 2, you have the element 1. Now 1 is less than 20. So since the 1 is less than 20, I will say the next greater element is going to be 20. Okay. So therefore you are getting here 20. Now before proceeding ahead, I will just push 1 to the stack. Let us now proceed to the index 1, which is 12, which have the element 12. Now we will see the 12 compare with the top of the stack. Now 1 is less than 12, so therefore 1 is useless for me. So I will just pop it. Is my 20 greater than the 12? Yes. So therefore 20 will be my next greater element. Okay, so therefore you have 20 as it. Now before proceeding ahead, I will push 12 here. Now I will go to the index 0. You have 7. Now 7, is 7 less than 12? Yes. Therefore 12 will be my next greater element, and therefore you have 12 here. And now I will just push 7 for future comparisons. So it is the algorithm which is followed here. Did you understand? Okay. So finally, let us go to the code. So stack, I am initializing a stack and answer array, and I am just going to iterate from the right of the array. So n minus 1 to 0. So while my stack is not empty and my current element, it should be greater than equal to stack. If it is greater than equal to stack dot top, that means basically the top of my the elements which are present at the top of the stack, they are useless. That means they are less than the current element. So therefore they are definitely not the candidate for the next greater element. So I will basically pop them all. Now if my stack is empty, then just put the stack dot top. That is answer I is going to be st dot top, and I will push the new element here. That is the current element. And by the way, I have already initialized the answer array with -1. So if the stack was empty, then -1 will be already present. And I will just return the answer. Is unders- understood? Is it clear?
Yes.
Okay. Is the concept of monotonicity clear? Okay. So you will have an assignment which is very similar, which is just a little modification of the next greater element. Any doubts throughout the entire lecture or any concept which is not clear? Any doubts?
There is no inbuilt monotonic stack.
Uh, Basically, monotonicity is just an algorithm. So there is no, as such, like there is no as such building for monotonicity.
Okay. Thanks.
Any other doubt? Anything which was not clear or something like that? Yeah, sure, you can go.
Could you repeat the second question of Q, I guess it was?
Okay, that DQ1.
No, of Q only.
Okay. Uh, like where you had doubts in that?
I didn't understand the question only, actually.
Okay. So first of all, the question is saying that you have to count the number of recent requests within a certain time frame. So you are basically you are given a ping request, and for every ping request you will have a particular time a time stamp. Now, what they are saying is that you have to, whenever you have a ping request, you have to check from the current timestamp till t minus 3000 how many requests were made between t to t minus 3000 to t. Okay, so between t minus 3000 to t, and you have to return the number of requests. Uh, did you understand your question?
Yeah, but like, how will we know how many requests were made?
Okay, so for that we have used queue. Like, let's say you are initializing a queue. So now whenever you are pushing the time stamp to the queue, I will just make sure that until my queue is not empty and my queue dot front less than t minus 3000. Basically, as I already said, here you can pretty much go to the example. I will, let's say this is just a treated as a queue. Now I will just say you are going to add new elements in the back of the queue. So like 100, 3001 and so on. So whenever a ping request is comes, so I will just add the new timestamp to the and to the rear, that is to the queue, right? Now in the front you will have all the old requests which may be lying outside t minus 3000. So I will just check where I will just try continue. I will use a while loop and I will remove all the requests which were beyond t minus 3000. So all my old requests will basically pop out. Like for example, here a new request has come 3002, right? So 3002 minus 3000 is basically 2. So I will just say, okay, my in the front of the queue I have 1. Now 1 is surely less than 2, right? So I will just pop 1. So how much elements are remaining? 100, 3001 and 3002. So that is the reason why we are just returning the queue dot size. So queue dot size is basically telling me how many requests are present in the current range. Is it now clear?
Yeah, somewhat clear.
Like, let me, let's say you are anchoring one. Okay. Now, after anchoring one, I will just check whether my any timestamp is there beyond 1 minus 3000, that is minus 2999, minus 299. Whether you have any time request which is beyond less than that. Currently, you don't have. Now, you will just put 100. So I will just enqueue 100. Now, I will just check whether any request less than minus 2900 is there or not. There is no, right? So again, here you will return 2 because 2 requests are present for now, which are lying exactly within the range. Okay, that is basically queue dot size. Now, in the third, you have 3001. Now I will just enqueue that, okay, and I will see all the, I will see right from the front whether they lie in the range or not. So 3001 minus 3000 is 1. So I will just check whether they lie in the range. So 1 is definitely lying in the range of 1 to 3001. So I will definitely not pop, and therefore you are getting the answer as 3 because you have 3 requests currently. Now 3002, if you enqueue it, now if you see 3002 minus 3000, it is going to be 2. Now 1 is less than 2, so it is a must to dequeue that. Now you have only uh, 3 requests, so you will return 3. I hope it is now clear from the example. Yes, yes, you can go on, continue. Is your doubt solved now?
No, actually, I think I should try that myself.
What? Okay. No other doubts, right? If there are no other doubts, I will end the meet. Thank you. Bye. Please solve the assignments which I will upload on Stack and Incubator.